The foundation of classic sorting algorithms at its core, sorting involves arranging elements according to predefined criteria, typically ascending or descending order. This fundamental operation has driven numerous algorithmic developments over decades, resulting in several widely used techniques suitable for diverse data scenarios. Bubble sort represents one of the earliest and most intuitive algorithms devised for sorting purposes. It operates by repeatedly iterating through a dataset, comparing adjacent elements and swapping them if necessary until the entire collection becomes ordered. While effective for small datasets, bubble sort suffers from poor scalability. Its quadratic time complexity means performance degrades significantly as input size increases, making it unsuitable for larger collections. Insertion sort follows a similar philosophy but offers better performance characteristics under certain conditions. By building up a sorted sublist incrementally and inserting new elements in their correct positions, it demonstrates superior efficiency when dealing with partially ordered data. Bubble sort works best for tiny datasets where simplicity outweighs performance considerations. Insertion sort excels with nearly sorted inputs, exhibiting near-linear runtime in favorable conditions. Selection sort introduces another variation by focusing solely on finding minimum values rather than comparing every pair of elements. Although conceptually straightforward, its constant factor advantages make it preferable in some constrained environments despite sharing similar asymptotic bounds with other simple algorithms. Divide and conquer approaches for scalable solutions. As we transition towards handling increasingly large datasets, traditional comparison-based algorithms become inadequate. This limitation has led to the development of sophisticated divide and conquer strategies capable of processing massive volumes efficiently. Quicksort emerged as a groundbreaking technique by leveraging partitioning mechanisms to recursively break down problems. Through cleverly selecting pivots and rearranging subarrays, it achieves average case performances comparable to O(n log n), outperforming many alternatives in practical settings. MergeSort adopts a complementary strategy by splitting datasets into smaller pieces, sorting independently, then merging results back together. While requiring additional memory overhead compared to in-place operations, its guaranteed O(n log n) performance makes it particularly robust against pathological inputs. Both Quicksort and MergeSort demonstrate remarkable versatility. Their implementations can be adapted to work effectively with various data structures, including arrays, linked lists, and even external storage mediums. In situations where stability matters, a critical consideration when preserving relative ordering relationships between equal elements, MergeSort proves invaluable. Its natural stability property ensures predictable output patterns without sacrificing efficiency gains achieved through divide and conquer paradigms. Specialized variants for unique requirements. Understanding general-purpose sorting methodologies provides only part of the picture. Real-world challenges often demand customized approaches that balance competing objectives such as speed, memory footprint, and implementation complexity. TimSort exemplifies this approach by combining features from both MergeSort and insertion sort. Developed primarily for Python's built-in sorting capabilities, it excels at handling real-world data distributions characterized by runs of already sorted sequences. HeapSort presents another compelling alternative by utilizing binary heap structures to achieve O(n log n) time complexity with minimal auxiliary space requirements. Its single-pass nature also facilitates easy conversion into a selection algorithm variant. Radix sort distinguishes itself through non-comparison-based methodology, relying instead on digit-by-digit grouping principles. This approach enables linear time sorting for integer values within defined ranges while demonstrating particular effectiveness when working with string data. Variations like bucket sort further expand our toolset. By distributing elements into appropriately sized containers before applying secondary sorting techniques, these methods offer optimized performance for certain distribution patterns encountered frequently in practical applications. Handling complex data structures effectively. Classical sorting algorithms generally assume homogeneous numeric data. As we encounter increasingly complex information representations, Adapting these techniques becomes necessary to maintain utility across diverse application domains. When working with composite objects containing multiple attributes, custom comparator functions enable flexible sorting behaviors. These allow developers to define prioritization schemes based on any combination of properties deemed significant for the task at hand. Linked lists introduce unique challenges due to lack of direct random access capabilities. Specialized adaptations must therefore account for traversal complexities inherent in these structures, often leading to modified implementation strategies that preserve original algorithmic characteristics. Tree-based structures present another interesting dimension. Binary search tree traversals naturally produce sorted outputs, suggesting potential optimization opportunities worth exploring for specific problem spaces. Distributed computing environments impose additional constraints requiring novel approaches. Techniques involving partial ordering and consensus protocols have gained traction for coordinating sorting efforts across geographically dispersed nodes. Performance considerations across scenarios evaluating sorting algorithm efficacy goes beyond mere asymptotic analysis. Practical deployments require considering factors like cache utilization, branch prediction accuracy, and memory alignment impact on instruction pipelining efficiency. Data locality plays a pivotal role in determining runtimes. Algorithms that process contiguous memory blocks tend to execute faster due to reduced page faults and improved CPU caching behavior. Time complexity measurements alone cannot predict execution durations accurately in real-world scenarios. Constants hidden behind big O notations can dramatically influence overall performance when applied to concrete instances. Space complexity considerations remain equally important, especially when dealing with resource-constrained devices. In-memory operations must carefully manage auxiliary storage requirements to prevent excessive overhead penalties. CPU architectures featuring vector extensions provide intriguing optimization avenues. Modern processors equipped with SIMD instructions enable simultaneous processing of multiple data elements, potentially accelerating certain sorting operations significantly. Emerging trends and future directions. The field of sorting continues to evolve rapidly alongside advancements in computer science research. Several promising directions suggest transformative changes that could redefine our current understanding of ordering mechanics. Quantum computing introduces fascinating possibilities for rethinking traditional paradigms. Quantum sorting algorithms leverage superposition states to perform comparisons simultaneously, theoretically achieving exponential speedups over classical counterparts. Machine learning integration opens up exciting frontiers by allowing adaptive sorting decisions based on empirical observations rather than predetermined rules. Predictive models can identify optimal algorithms dynamically suited to incoming data streams. Hardware-specific optimizations represent another emerging area. Tailoring sorting strategies to exploit architectural features like NUMA layouts or GPU parallelism promises substantial performance improvements for specialized computing platforms. With increasing emphasis on energy efficiency, there's growing interest in developing low-power sorting techniques. These focus on minimizing computational intensity while maintaining acceptable levels of correctness and reliability. Conclusion: the landscape of sorting algorithms reflects a rich tapestry woven from mathematical elegance and engineering pragmatism. From fundamental principles underlying elementary methods to cutting-edge innovations shaping future developments, this journey showcases the enduring relevance of ordering operations in computational contexts. To truly master sorting techniques, practitioners should experiment extensively with diverse implementations, benchmark thoroughly under varying conditions, and stay informed about ongoing research breakthroughs that continually reshape our conceptual framework for data organization and transformation.